Hey everyone, and welcome back to Central Physics Reviews. In the last episode, we talked about how some systems in the real world have more than 3 degrees of freedom, because not only can they move around in the 3 spatial dimensions, but they can also rotate and change their orientation with respect to at least one axis. We also talked about the mathematics we need to go from the angular acceleration alpha over here to figure out the rotational trajectory of our system, meaning its angular velocity and angular position as a function of time. And that process, that mathematics, was called kinematics, just like it was in the case of linear systems, moving translationally. But we're still missing a huge piece of this puzzle, which is how do we actually figure out what the angular acceleration of our system is going to be, right? If we think back to when we were just talking about translationally moving systems, we had a complete flowchart of how to do physics, right? We list out our interactions, and from those we can figure out what forces act on our objects by invoking the laws of physics, right? Those laws of physics told us precisely what force corresponds to what interaction. Then we can figure out the acceleration of our system from the force just by knowing the object's mass, right? Because F equals ma, Newton's second law. And finally, we can do kinematics again to go from the linear acceleration, a, to the linear trajectory, so the velocity as a function of time and position as a function of time. So what we want to do in this episode is actually figure out what the analogous flowchart is for rotational motion. Now, those of you who've seen this before already know how this is going to go. There's going to be some new quantity labeled by the Greek letter tau, and that's called torque. And the torque is going to play an analogous role to the force in linear motion. So it'll tell us this angular acceleration as long as we know or have a measure of the system's resistance to angular acceleration. So that quantity is going to be called the moment of inertia, and it's given the symbol I. And it plays the exact same role that mass did in the case of linear motion, because the equation of motion that we use to get our angular acceleration is torque, tau, equals the moment of inertia, I, times the angular acceleration alpha. So already you can see the analogs that we can draw to Newton's second law, F equals ma. Now the next question we have to ask is, how do we figure out the torque that's acting on our system, right? Do we need some new laws of physics to tell us what torque results from certain interactions with the external world? And the answer is actually no. Torque is a mathematical quantity that can be found from the same forces that tell us how the system will accelerate linearly. So there's an arrow here from forces to torques, and the way you go from a force to torque is by taking into account where the force acts on an object. In other words, the position at which that force is applied. And that certainly makes intuitive sense, right? If you're trying to open a door, you can push it far away from the hinge and it'll rotate open, but if you push it at the hinge, it won't swing open at all. So this idea is consistent with our experience in the real world, but it's still extremely vague, and most importantly, I haven't told you what exactly torque and moment of inertia are. So in this video, we're going to talk about fundamentally where these two quantities come from. And in fact, I'll show you that just by looking at the forces acting on our system and where those forces are acting, we can derive the formula tau equals I alpha that gives us the angular acceleration of our systems. And that's actually a calculation that I haven't even seen in any lectures or textbooks, so stay tuned for that because it's really short but really cool. But first, I want to tell you about why we should even expect forces, which govern the linear acceleration of our system, to be able to tell us anything about the angular acceleration of that system. And fundamentally, that's because rotation is secretly translation in disguise. Right? When you have a rotating object, like this disk I drew here that's rotating counterclockwise, what we really mean when we say it's rotating is just that all of the particles that make up this disk are moving in circles, coherently, such that overall the disk doesn't change shape and the disk may not even move as a whole, but this coordinated translational motion is occurring at every point on the disk at the same time. And that allows us to describe the rotation of this disk in terms of just one number, its angular speed, omega, instead of having to worry about specifying every single velocity vector for every single particle that makes up the disk. But because fundamentally all of this motion is translational at its core, we can actually use forces that give us the linear acceleration of these individual points in order to figure out how the object as a whole will accelerate its angular speed. So let's talk about some connections between rotational and translational quantities. So let me erase these arrows and draw a single point over here. And let's say that point is some distance r from the center of rotation. How can we relate the velocity of that particular point to the angular velocity of this object as a whole? Well, the easiest way to think about it is to just realize that whenever this object moves along its little circle of radius r by a small angle, let's call that angle d theta for an infinitesimal angle theta, then the distance it travels in that same time period, which we'll call ds, is going to be related geometrically to the angle of that arc, right? The distance covered is going to be equal to r d theta. That's simply the formula for any arc length in geometry. And what this tells us is that the velocity of our object, v, is just going to be equal to ds dt, right? How much distance is covered per unit time. And because r is constant, since it's moving in its own little circle, it's just going to be equal to r d theta dt. And we have a variable for d theta dt, that's just the angular speed, omega. So in fact, if you know the linear speed of any particle on this disk, you can automatically tell me the angular speed of the disk as a whole. Now, what we really want to do is relate forces to angular accelerations, or equivalently, we want to relate linear accelerations to angular accelerations. So let's take another derivative, right? We get that the acceleration of this object, or of this point, I should say, is equal to dv dt. And again, r is a constant, so we get r d omega dt. And we have another variable for that, because of course we do, we're physicists, we call that alpha. The angular acceleration is the rate of change of angular speed. So now very quickly we've derived this relationship between the linear acceleration of any point on this disk to the angular acceleration of the disk. But if you think about this a little bit, we haven't actually been very careful with this derivation because we didn't take into account how the direction of velocity was changing with respect to time, right? This variable a is only measuring how fast the speed or the magnitude of velocity is changing over time. So really what we just calculated is the tangential acceleration. And if you don't remember exactly why that's the tangential acceleration, we talk about that in more detail in our centripetal force video back in episode 8. Anyway, this is the kind of simple derivation you'd probably see in a first class on rotational motion. But here at Central Physics Reviews, we like to be a little bit more thorough. We like to completely take account of all of the directionalities of our velocity and acceleration vectors. That's just the cool physicist's thing to do. So let's go ahead and redo this work, starting from step 2, calculating the velocity, but now accounting for directions, right? So we have that the velocity vector is still going to have r omega as its magnitude, but now its direction is going to be something that's perpendicular to the radius, right? Perpendicular to this radius vector, right? Because it's moving tangentially in a circle. It doesn't have any other components. And we also know that it's going to be perpendicular to n hat, which is the normal vector we defined in the last episode that just points in the direction of our axis. So in this case, n hat points out of the page. So obviously all of the points on this disk are going to be moving perpendicular to that because they're moving within the plane of the page. And those of you familiar with cross products might realize that if you know velocity is perpendicular to two different vectors, you can actually specify its direction by taking the cross product of those two vectors. So in fact, we can write the direction of this velocity vector as the cross product of n hat, the axis vector, with r hat, the radius vector. And you can check that for yourself with the right-hand rule, right? N hat points out of the page, and the radius vector points toward this point, like this. So if you curl your fingers from the out of the page direction into that radial direction, your thumb will point in this direction, which is exactly the velocity vector of a point at that position. Now there's actually one more way to simplify this notation, which is to absorb this radius magnitude into the radius unit vector to just get the radius vector, r vector, and then to also define something called the omega vector, which is simply the n hat vector, but now with a new magnitude omega. And by making those two substitutions, we have that the velocity is simply equal to the cross product of this omega vector we just defined with the r vector. Now, full disclosure, just like I said in the last episode, this angular velocity isn't a true vector because it's not really pointing in any direction with a particular strength. In fact, it goes by a couple different names. Some people call it an axial vector because it just represents the direction of an axis according to the right-hand rule. Other people call it a pseudo-vector because it's kind of pretending to be a vector in disguise. But either way, we can treat it as a vector when we're doing mathematical calculations like this, and it provides a nice shorthand for that purpose. And in fact, that's going to make our job of finding the acceleration vector here a little bit cleaner, because now all we have to do is apply the product rule, and we find that the acceleration is equal to d omega vector dt cross r vector plus omega crossed with dr vector dt. And of course, we can substitute in the definition of these derivatives, and we'll find that it's equal to alpha vector, which is d omega vector dt cross r, plus omega cross v. Now, this first component is exactly the tangential acceleration that we found before, right? This is just magnitude r alpha, and the direction is alpha cross r. So if you do the right-hand rule again, you'll find it goes tangentially to the motion, which I'll call v hat because it's in the direction of our velocity. And this other component you'll recognize as the centripetal acceleration, right? The magnitude omega v is the same as v squared over r if we make the substitution that omega is v over r. And the direction of omega cross v we can find by taking the right-hand rule and curling our fingers from the axis of rotation out of the page into the velocity vector to the left, and we'll find that our thumb points toward the center of the circle, or in the direction minus r hat. So this is the complete expression of the velocity and acceleration of any point in this disk, knowing just how far away it is from the center and what the angular or rotational quantities are. So if we know omega and alpha, we can find v and a for any point. Now, I want to show you that we can also do the opposite. We can find the angular acceleration just from knowing the linear acceleration, or in other words, just from knowing the force. So let me show you how we can do just that. I'm going to start by taking you through the process for a very simple system on the left. It's just a simple blue particle over here, connected to some sort of origin with a string so that it can only move in circles around that central point. Now let's say we know the force acting on this particle, so we can draw some vector f. And what I want to show you we can do is find its angular acceleration just from the force. And to do that, the first thing that I'm going to do is write down the quantity r cross product f. And the reason that I start out by doing that is because we can rewrite this as the mass times r cross a, and r cross a is a super useful quantity because that cross product gets rid of this entire centripetal acceleration term, since the cross product of r vector with r hat is 0, they point in the same direction. That means that after this cross product is done, the only thing that we're left with is the cross product with this tangential term, from which we can extract the angular acceleration alpha. So check this out. What we're going to get is the mass times the cross product between r and r alpha v hat. And the first thing we can do is actually find the magnitude of this cross product, which is just going to be mass 2 factors of r and a factor of angular acceleration, right? And we're not going to have any sine theta that goes into these cross products because the radius and velocity vectors are perpendicular to each other. So the only thing that's left to do is find the direction. And the direction of r cross v, if you do the right-hand rule again, is going to point up out of this page in the direction of our axis. And like we've done before, we can combine alpha and n hat to define an axial vector, or a pseudo-vector, alpha. So we get mr squared alpha vector. And from here, we're basically done, because now we can solve for the angular acceleration vector. It's just going to equal r cross f divided by mr squared. Right, so just to tie this back to our original goal, we've actually taken the force, which we know corresponds to linear acceleration, and we've used it to not only find the linear acceleration of this particle, but also the angular acceleration of our system. So we don't need any new laws of physics after all. But that was just a baby example, right? That system consisted of only one particle moving in a circle. What happens when we have an actual real-world object rotating around some axis? Well, we can actually derive a really similar result. We'll start pretty generally by assuming that there can be forces exerted on this object at any one of its points. So there can be a force here, there can be a force there, There can be a force down here, anywhere you like. In fact, mathematically what we're going to do is we're going to assume that there's some force, it could be zero, but generally we're going to assume that there's some force acting on every point of this object. So because there are infinitely many forces for infinitely many points, each force is going to have to be infinitesimal. So a natural quantity to start out with, instead of r cross f, is the integral of r cross df, right? We're basically going through each infinitesimal force, taking r cross that force, and adding it up. So this might look a little bit complicated, but don't worry, we'll simplify it in just a bit. For now, what we have to realize is that each infinitesimal force is going to correspond to an infinitesimal mass, dm, and the mass is infinitesimal because the force is acting on one infinitely small point, right? So we have dm multiplying the acceleration at that point, a of r. So we can rewrite this integral as r cross a of r dm. But we already know what r cross a is, right? We can plug in that r cross a is just equal to r squared alpha vector. So we get r squared alpha vector dm. And the cool thing is that because this object is rotating as a whole, the alpha vector doesn't depend on which point you're talking about, right? All of those points correspond to the same angular acceleration. So we can pull that out of the integral, and we're left with integral of r squared dm. And now we can actually straight up solve for our angular acceleration vector alpha. It's the integral of r cross df divided by this other integral of r squared dm. And by comparing it to the angular acceleration we found for the point on the left, you can see that this expression is really just a generalized version of the other one. Now, because we're physicists here and we're not mathematicians, we still get scared by these mean-looking integrals. So instead of keeping them in this form, we just give them a variable name and call it a day. So the integral on top, the integral of r cross df, is going to be what we call the torque vector, which we label with the Greek letter tau. And the integral on the bottom is going to be what we call the moment of inertia, labeled with the letter I. And in fact, if you just flip a couple of things around, you'll get the formula that I mentioned at the very beginning of this episode. Tau equals I alpha. And in fact, when we're dealing with rotation about just one fixed axis, you don't even need these vector signs because we both know they point in the same direction. They point along the axis. And you can realize that the torque also points along the axis just by thinking about this cross product between r and our forces, right? Because both of those vectors are in the plane of the disk here, their cross product is always going to point perpendicular to that disk or along the axis. Now, there's good news and bad news. The good news is that we almost never have to do this top integral because usually we don't have a force acting on every single infinitesimally small point of our object, right? Usually we just have a couple finite forces acting at specific points. And because they act at specific points, every one of those forces is going to correspond to a constant radius vector r. So at each of those points, the integral of r cross df can actually be simplified as r cross the integral of df. And of course, the integral of df is just the total force at that point, right? R cross f at that position. So if you have multiple forces, you'll just get multiple terms that look like this. So the torque, instead of treating it as an integral, can really be thought of as a sum over all of your forces of this quantity r cross the force at that position. So that's the good news. The bad news is that every object has its own moment of inertia, and in most cases, we're going to have to either do this integral on the bottom by hand, or memorize what that integral is for different geometries. So for example, I've memorized by now that if you do this integral for a disk, you'll get that the moment of inertia is equal to 1/2 m times the radius of that disk squared. And I'll show that to you pretty soon. But unfortunately, it's not always as simple as finding the torques. Okay, so this was the derivation part of the video. We derived tau equals I alpha. What we're going to do now is actually jump into some examples about how we might calculate torque and moment of inertia for certain systems. So let's go ahead and start with torque. Now, as a physicist, I personally don't get out very often, but I want to make these examples as relevant as possible for you, the viewer. So here I've imagined a typical situation in which a normal person might find themselves on an average day out, right? So here's how this goes. Let's say you're going on a walk through the woods, and all of a sudden you bump into a stock image of a wooden log. You think to yourself, wow, that's a really cool log, and I happen to be carrying around a really big nail that perfectly goes through the center of this log. I wonder what'll happen if I use this nail to pin down this log right at its center. And of course what'll happen now is that the log as a whole won't be able to move anywhere, but it'll still be able to rotate about that pin. So we go ahead and we try to push this log. We exert a vertical force on its edge right over here. Let's call that force F. And in order to figure out how this log is going to rotate over time, the first thing we want to do is find the torque corresponding to that force, right? So we have this equation that torque is the cross product between R and F. We know what F is, we're applying it, and we know which direction we're applying it in. And R is just the vector that always points from the center of our rotation, so from this pin, toward the point of contact. So it's going to be this vector right here. This is going to be R, right? Now let's not forget that our torque is a vector in and of itself, and the direction of that vector is going to be determined by the right-hand rule between R and F. So if we start pointing our fingers in the direction of R, and then we start curling them toward F, what we'll find is that our right thumb points up out of the page. And so what that tells us is that the torque vector is going to be some magnitude with its direction pointing out of the page, which I'm just going to call z hat. So let's say the log is in the xy plane, out of the plane is going to be the z direction. Now the magnitude of a cross product is just given by the magnitudes of these two vectors, rf, times the sine of the angle between them. So to find that angle, what we would have to do is start the force vector F and the radius vector R at the same origin, and then this angle is the one we'd have to take the sine of. Of course, you can tell by looking at the picture that the angle I just drew is actually going to be equal in size to this angle between the vectors right here. So if you happen to bring a protractor with you on your walk through the woods, you're all set and you've just found the torque. Now, if you don't happen to bring a protractor with you, because you're a theoretical physicist and you don't bring experimental apparatuses with you, one thing you can do is realize that the torque is going to be biggest when sine theta is equal to 1. And sine theta is equal to 1 when theta is equal to 90 degrees. So if you want this log to rotate as fast as possible, what you can do is simply exert your force in a perpendicular direction to the radius vector we drew. In other words, instead of exerting it vertically, you could exert your force up and a little bit to the right, like this, forming a right angle between the two vectors and maximizing the torque you exert on the system. The last thing that I'm going to say about this example is that you should watch out for what happens if you exert a force on the other side of the log. Let's call this F2. Intuitively, we know that this force is going to try to make the log spin the other way. And the way that actually comes into the math is that when you take the cross product between R and F, when you actually apply the right-hand rule to these two vectors, let's call this R2, you'll see that the torque doesn't point in the z direction anymore. The torque from the second force, which I'll call T2, is going to be some magnitude that points in the minus z hat direction. And because rotation is always defined as being counterclockwise relative to some axis, then the fact that your resulting angular acceleration is going to go in the minus z hat direction is actually what tells you that this second force would cause rotation in the opposite direction. And of course, if you were applying a force on both sides of this log, then you'll find that these two torques actually act against each other, right? One is in the z direction, one is in the minus z direction. So adding them up actually reduces their total magnitude. And you can use that math to figure out what the torques have to be in order for there to be no net angular acceleration, because the two torques will perfectly cancel out. But I'll leave those calculations for you to experiment with on your own. For now, we should talk about moments of inertia. So if you remember that first example we looked at initially with a single particle rotating in a circle around a fixed origin, we found that the angular acceleration vector for that system was equal to r cross f divided by mr squared. But that's actually just a specific case of the more general formula we derived later, because the moment of inertia for this system, which is the integral of r squared dm, is actually really simple. all of the mass is concentrated at a single radius, capital R, from the origin. So this factor of r squared can be factored outside of the integral, right? We'd end up with capital R squared times the integral of dm, and integrating that infinitesimal just gets you the total mass. So we're left with mr squared. And then we can plug that into our general formula of angular acceleration equals torque over moment of inertia and get the same thing we found before. In fact, something really similar happens if we look at a whole ring of mass m centered at the origin, right? So this second example in the middle here, you can think of like a hula hoop or something like that. In this case, the moment of inertia, which is defined as the integral of r squared dm, also simplifies in the same way because all of the mass is the same distance from the origin. So we can still write that it's the integral of r squared, or it's just capital R squared times the integral of dm, and that's still equal to mr squared. And so you can use that in combination with whatever torques act on this hula hoop in order to find how it's going to angularly accelerate. Finally, we can look at the more complicated system that I mentioned earlier, which is a disk of the same mass m, but now the mass isn't concentrated all at the same distance from the origin, so we can't do the same simplifications we've done in these previous two cases, right? So we can write out that the moment of inertia is still defined as the integral of r squared dm, but here we have to be a little bit more careful about how we evaluate this integral. One thing we can do is we can actually rewrite this infinitesimal mass dm as a mass density, or a mass per unit area, times an infinitesimal area. So that is dm is going to equal sigma, a mass density, times an infinitesimal area. And then the moment of inertia becomes the integral of r squared sigma dA. So this integral tells us that we have to take a sum over all of the infinitesimal areas in this disk. Well, there are two things we can do to further simplify that integral. The first is if sigma is a constant, in other words, if the disk has constant density everywhere, we can factor it outside of the integral, just to make things a little cleaner. And then inside the integral, we can replace a small amount of area dA with the equivalent expression r dr d theta. And the reason that those two are equivalent is because you can draw an infinitesimally small area of the circle, which has this shape. So I've drawn it quite big, but imagine that it's infinitesimally small. It starts some radius r from the origin, it extends some radius dr, and it spans some angle d theta, right? Then the dimensions of this slice of area are dr along one side and r d theta along the other side, because that's how you calculate an arc length corresponding to that angle. So if you multiply dr by r d theta, you get the area of that small segment. So bringing that back to our integral, we now actually have to do two integrals, right? One integral, with sigma on the outside, is going to be over theta, and the bounds are 0 to 2 pi, because we're doing a full circle. So we have d theta in that first integral. And the second integral we're going to do between 0 and capital R is going to be r cubed dr, because now we have three factors of r stuck in there. So doing out the calculus gives us sigma times 2 pi on the first integral times capital R to the fourth all over 4 in the second integral. And now the last thing we have to think about to simplify this is if sigma is a constant, it has to just be equal to the total mass divided by the total area, which is pi r squared. So if you substitute sigma equals m over pi r squared into this equation, what you'll end up with is the moment of inertia equals 1/2 mr squared, as I promised you before. So on one hand, that integral was a little bit harder to do than the others, right? It was a little bit less straightforward. But on the other hand, from now on, if you ever see a disk with a constant mass density, you can automatically know what its moment of inertia is without having to do any integrals at all, because the moment of inertia is just a geometric quantity. It's 1/2 mr squared. No matter what material your disk is made of or anything else, if you know its mass and its radius, you're all set. Except there is one caveat to that, which I should tell you about, and that's when we write down this formula, that the moment of inertia is equal to the integral of r squared dm, this variable r doesn't refer to the distance from the center of mass necessarily, right? It just refers to the distance from the center of rotation, whichever point your system is pinned on. What that means is if our disk, for example, wasn't pinned at the center, but instead was pinned at a point along its edge, its moment of inertia would be different from 1/2 mr squared because you're not actually doing the same calculation anymore. The good news, though, is that if you already know the moment of inertia of a system about its center of mass, you can actually find its moment of inertia about any other parallel axis by a theorem called the parallel axis theorem. And this says that the moment of inertia through some axis, which is parallel to some other axis through the center of mass, is equal to the moment of inertia about that center of mass axis plus the mass of your system times the distance squared between the original axis through the center of mass and the parallel axis which is offset from it. So in our example, where we moved the axis from the center of a disk to its edge, its moment of inertia would change from 1/2 mr squared to 1/2 mr squared plus mr squared, because that distance we moved the axis is equal to r. So in a lot of cases like this one, even if you're rotating about a point that isn't your center of mass, you might be better off finding the moment of inertia through the center of mass and then just using that theorem to find the new moment of inertia you actually need. So now that we've gone over how to calculate torques and moments of inertia, you should be ready to compute all of the angular accelerations you like. And hopefully now you have a better understanding of the full idea of how physics works, going from just a list of interactions we have to how things accelerate not only linearly, but also rotationally. If you want to learn about even more aspects of rotational motion, like angular momentum, rotational kinetic energy, and even rolling, stay tuned and be on the lookout for the next few episodes of Central Physics Reviews.